Character encoding is a topic that causes both young developers and mature ones to take a step back and get very perplexed at the topic. And indeed, this topic is complex because you see, there are so many encodings, and you can get the message in one encoding and try to open it in another encoding. And how do you decide what is the actual encoding? The history of character encoding is super important in order to understand this. We have so many character encodings. Yes, we do have the Unicode, but we also have the ISO 8859, and we also have ASCII, and in the Unicode, and we have UTF-8 and UTF-16, and God knows what else. So let's explore the basics of it, what you need to know in order to feel pretty safe about it. And this is the topic of this episode, character encoding. So let's get going. First, I would like to stress out that character encoding or words encoding did not begin with computers. Right now, as I'm speaking to you, or as you speak to your friend, you are encoding your ideas, you are encoding the characters in voice. This is a sound wave. You have just made a character encoding in the human voice. Okay, you have taken the representation, like the aplatonic representation of the letter A, converted it to voice waves and transmitted it via the air into another person. Okay, so here we have a natural character encoding. And this does not end there, because we also have many other codes also before the invention of the computer. Yes, we have Morse codes, and in Morse codes, you see, we have another kind of encodings to the characters. So we have already have many encodings, and it's quite a must to encode stuff, as we want to pass and transmit this information from one entity into another. And also in computers, when you type a key, when you key press a key in your keyboard, you need to encode it someone. The physical key press, you need to encode it into some kind of electricity and transmit it to computer, so he would understand the physical key press that you have made on the keyboard. And this is where character encoding in computers, in the context of computers, comes in, and this is what we're going to explore. And I think that we'll start with the ASCII character encoding. The ASCII is an acronym for the American Standard Code for Information Interchange. It is a code for representing 128 English characters, such as numbers. With each letter, it's assigned to a number from 0 to 127. That's very small, because it's focusing on English. For example, the ASCII code for an uppercase M is 77. Most computers use the ASCII code to represent text, which makes it possible to transfer data from one computer to another. Here are a few more examples of the ASCII codes. So, as you remember what we have said, that encoding is simply the representation of a letter, in our case, because we're dealing with characters or signs, by numbers. So the space in ASCII is 32. The exclamation mark is 33. The asterisk is 42. And so forth. The large letter A, the capital letter A, is 65. And that's it for ASCII. It's simply 128 characters, English characters, that are represented by numbers. But what about the additional languages, such as the European languages? The ASCII is focused on the English characters. It is 128 characters, 128 numbers that represent the English characters. 128 is 7 bits. So you have an additional bit in a byte in order to represent additional characters. And this is exactly what the Europeans' characters are used. They're utilized by the 8th bit, which allows us to get a multiplication of 2 of the amount of characters that we have in the ASCII. And so there was gave birth to the Windows 1252, the ISO 8859, and all those ISO 8859-15 Latin 1, all those is an 8-bit character encoding that extends the 7-bit ASCII encoding scheme, and it's used to encode most of the European languages. For example, the ISO 88591 is known as the Latin one, and it's mostly used in most of the common English European languages such as the German, the Italian, the Spanish, and the French. It's very similar to the Windows 1252 encoding scheme, and all these schemes just extend the ASCII. They utilize the additional bit in order to represent all the European languages. And of course, when you receive a message, you need to know what is the encoding. If it's Latin 1, then you treat it in one way. If it's ISO 8859, then you treat it in another way. If it's Windows 1252, you treat it in a different way. If it's ASCII, you treat it in a different way. So you get the numbers via the wire into your computer. You then understand, you then unpack the request, see what is the character encoding, and according to this, you convert the numbers into characters and you present them on the screen. The Unicode was created in order to have a single character set that includes like every possible language. Okay, the Unicode itself does not specify how many bits we have, and actually the Unicode is like an abstraction. It is saying you have the Platonic letter A, okay, the letter A in your brain, and while you could code it with your voice, I will give you a number, and this number will uniquely identify this letter. This number, so they have a set of numbers in the Unicode, simply very simple, okay? You just decided, I want this number to represent this letter. I want this number to represent this sign. And then when you see on the web or on an application, there is a standard to represent it, like U plus, and then let's say 0671. The U plus 0671 is the number that represents this character. And that's it. So if you want to represent a word, you concatenate multiple U plus number, U plus number, U plus number, where each number is the hexadecimal representation of the number. And now that we have an abstract numeric representation of the numbers, we need to actually encode it into the computer because the computer does not like understand the Unicode. It understands the actual encoding of the Unicode number. And for the actual encoding, it's like a tree. You have in the root the Unicode, and then you branch into multiple implementations of the encoding. It's like the interface where you defined what is the number, what is the abstract number that represents a character. Then you have the implementations of how to represent these numbers. And as you can guess, you can have multiple implementations. So if you are representing like the English letters with the Unicode, you are going to end up with many zeros because most of the English letters are like on the basics. It's like the ASCII, it's like the 65 is 8. You don't need like 0065. Therefore, the UTF-8 was invented. And what it's saying is that if you have a Unicode code point from 0 to 127, then it's stored in a single byte. And only Unicode characters which have the representation of the number above 188 will use multiple bytes. And actually, it's not only limited to 2 bytes. The UTF-8 can be 2 bytes, 3 bytes, or even up to 6 bytes, depending on which character you represent. And for the implementation of the Unicode, we have multiple encodings. We have UTF-8, we have UTF-7, we have UTF-16, and whatnot. So for UTF-7, we are saying, hey, we are in English. We are not interested in all the additional zeros that exist in many Unicode characters, because the number is assuming that you need tens of thousands of characters, but we are in English. We only have a few. So UTF-7 will assume that we are having zeros because on the top of the character, because we are simply using English letters. So we're encoding them. It's enough to encode them with 7 bits. So if you give me a number and you tell me this is UTF-7, I know that this number represents most likely an English character in the Unicode. And the number, what's important to know is that the actual number that we are going to have is the same number as in the Unicode. Okay, it doesn't matter if it's UTF-7, UTF-8, UTF-16. The number itself is represented, and when you decode it, you get to the same Unicode number. Okay, the Unicode number is the actual number. When you decode the UTF-7, you get to the same number that you have in Unicode. In UTF-8, they said, okay, we could assume that in most of the times we are going to have English letters, but if not, then we are going to add multiple bytes. So in UTF-8, it could use 1 byte, but it could use also 2 or 3 or up to 6 bytes, because it's saying in most of the times we're going to use single byte in order to represent the letters. But if we are going to use a bigger number, then we are going to use multiple bytes. And in UTF-16, we are simply using the constant value of 2 bytes, 16 bits, right? And that's it. You have the Unicode where you have mapping of permanent numbers. A number represents a character, and there are a lot of them, tens of thousands. And then you have the implementation, because this was the interface, the Unicode. And the implementations could be UTF-8, where in most cases you say, I'm English, I don't really need all the numbers. But there could be cases where I would need additional numbers above the 8 bits. So I would send 2 bytes, 3 bytes, or 3 or 4 or 5 or even 6 bytes, okay, in UTF-8. UTF-16 is just saying, okay, I'm going to have 2 bytes for it, and it is also called with the UCS2. So that was it for Unicode and for UTF-8 and for UTF-16. The important thing to know is that Unicode is the abstract number that represent the character. UTF-8 and UTF-16 is the actual encoding on the computer. So you have like 2 layers. One layer is the abstract number, and another layer is the actual implementation. And with that, we close our episode about character encoding. I hope you enjoyed it as much as I do, and I will see you next time. But what about non-English characters? We said that for English, it's enough to have the first 7 bits. So if you are a non-English speaker and you have non-English characters, then we could utilize the additional 8th bit. And when we utilize it, we gain another 100, and from now 128, the number, 2 additional numbers up to 255. So we could use these numbers. And when we use these numbers, we could just assign a number like, let's say, 130 into a character in your language, in your different language, like Greek. But then there are other languages, and they all can abuse this interval of numbers. They can use, so you could use it for Greek, and you could use it for let's say Spanish and for German. But so you could use the 130 to represent a different character in German and a different character in Greek. So how do you tell if you receive the message with this character encoding, if it's in characters in German, in Latin, or whether it's characters in Greek? The way to do this is that you send additional parameter which says what is the code page. So you said my code page is called blah blah, and this would mean that the additional characters from the number 128 refer to this language. So we are passing another parameter. It's like one global parameter that we are passing that specifies what are the additional characters. So every text that you have in the computer is represented by some kind of encoding. It could be UTF-8, it could be UTF-7, it could be ASCII. You need to know what is the encoding of the numbers because you need to translate from the number into a character.